Okay, so we got another LeetCode question here. This one's an easier one. However, the fun thing with some of these easy ones is trying to find ways to optimize it beyond just the big O time and find minor optimizations that let you find some other ways to essentially speed up your code. Um, So I think easy questions, like unironically, you can find a lot of little tricks in them. But the actual algorithm itself is a really good place to start, especially if you're new to getting back into the interview game for problems like this. And it looks like this is going to be another array problem, which is a good, one of the major sets we say arrays and trees are the main data structures. And looking at this, it looks like we're going to be doing some type of like lookup with this problem. But let's first go over the problem itself and see what we can do. So this is the daily question for the largest positive integer that exists with its negative. Given an array nums doesn't contain zeros, find the largest positive integer such that it's essentially its complement exists in the array. And then we return that max integer. And if nothing exists, we return -1. So what I'm thinking is essentially we can like loop through nums and we can essentially do a check if complement exists, and if it does, then return max of something like the like current max, the current number, and the like complement of current number. And what I'm thinking is the way to check it if it exists is if it doesn't exist, we add it to some type of hash like map or hash set. Um, so let's think through this kind of quickly. Um, so let's first start by creating our lookup table that's going to be just off by one with my typing. Integer, let's just call this elements that are going to be in nums, and it's going to be a new hash set. And what we can say is also our initial solution is going to be equal to -1. Um, and what we're going to say is for int I equals 0, I less than num's length, and iterate up. What we're going to do is we're going to first check if our set contains the complement. And if it does, let's just check these parentheses really quick. If the complement's in there, we're going to say solution is going to be something like the max of solution, and is it math.abs for the um I believe that's how you get the absolute value, and that's why we always have the positive. And that saves us doing like one more math max of nums I and negative nums I. Um, okay, so now let's do our else condition. And this is just going to be we add it to our lookup table. And this pretty basic. I'm fairly confident this should work. If there's no syntax issues, let's try that out. Syntax problem. Got a semicolon. Oh, helps when you return your solution. All right, cool. So we met the base case. Yeah, and we actually beat all the edge cases. Cool. So let's now think about ways we can potentially optimize this. So there's two things I'm thinking of. So we already have an O of n runtime, right? Like we're only looping over our n. So now this is kind of what I was saying is like with these problems, you kind of get the fun case of like, is there a way to make this uh like significantly more optimal than you would normally think, right? Um, so let's think of some plays so that we could potentially do it. So I guess one potential way we could save time is adding another if in here that essentially checks if the solution we're even checking would be um is like even a valid case, right? So let's make this an else if. And what we can say here is if solution is greater than math.absolute of nums I, then all we need to do is add, and we don't need to check these extra if conditions. And essentially what this is saying is like, hey, let's say this order was opposite where it's negative 3, 3. Like, we don't even need to do this logic for negative 1 and 2 because they're not even bigger. And then the other thing that we can do here is we can make a variable int abs I, which is going to equal math.absolute of nums I. And this will save a very little bit of time in calculating uh, this value a couple times. Um, like I said, a lot of this is just like super micro potential optimizations. Um, let's think what else we could potentially do. Ah, something else we can potentially do, and this might save a little bit of time, is what if we initialized our hash set so that we didn't need to take time to um like update its capacity if we just pre-allocated some of the memory for it. So we could do that by doing something like what's a syntax word? So do like an int to say how many we want, and it's gonna be something like nums length. And you don't technically want to allocate all of it, right? It's just something like 3/4 of the length in case there's duplicates. And this makes it so you hopefully you're only reallocating memory a couple of times. Oh no, I feel like this one might be pushing it for how we make stuff more optimal. Let's make sure these changes all compile. And let's submit. Didn't none of those save time. There's something else that we're missing. What else could we potentially do? Is there anything else in the description? Ah, constraints. So we can actually, this is going to require like refactoring the entire solution. But I think we can use this 1000 to 1000 thing to update it even more. Um, oh wait, let's do one more small optimization thing here. Let's do for num in nums instead. And this naturally will like go over the for loop and we don't even need to worry about iterating on I. So instead of wherever we do nums I, we're going to change that to just be nums. Or that's just going to be num, I think. Let's see if this saves us any time. But I don't think this is like the big optimization you can do. I think we can pre-allocate 2000 spaces and go from there. Let's double check that that is, where did I screw this up? Oh, I need to say int num. Did we beat 5 milliseconds? Nope. All right. There's still something else, and I think it's what I'm saying. So let's actually kind of scratch this hash set and instead pre-allocate it as a like Boolean array. And what we're gonna say essentially is this Boolean array is gonna be all the values from zero or from -1000 to 1000. So we're gonna have a Boolean array exist, and that's gonna be a new Boolean array of 2000. Actually, it's 2001 spaces, right? Because it's gonna be 1000, 0, -1000. And then we're gonna keep our int solution as -1. And how are we gonna loop over this? So instead, what we can say is we're still gonna do for int num nums. And what we can say is what can we do? Let's go back to the description. We know nums of I is not 0. Does that do us anything? I don't think so. So what we can do is check if our exists lookup has the complement of our value plus 1000. So like the value that's 1000 off of it. So you take the inverse of it, go 1000. Yeah, and that way it works because of us being at 0 to 2000. That's interesting. So from here we can then say if that exists, then our solution is going to be the max of our current solution and the absolute of our current number. And this is essentially what we had down here, if I remember. Math, max solution, and then our apps. So yeah, we have like the same thing. It's just we're looking it up using a pre-allocated Boolean array. And then what we do is if it doesn't exist, we say that that spot, typo down up here, at num plus 1000 is going to be equal to true. And really what this Boolean set is doing is -1000 to -999 all the way to 0 to 1 to 999 to 1000. That's essentially what this hash or what this Boolean array is representing. And what we're saying is each of these values, how do you go to the complement of it? Well, you take its inverse and you can add 1000. So let's just kind of think this over real quick. So the 0 index, 0 is -1000, should map to -1000. The 1 should map to -999. And then if we keep going, something like 2001 should map to 1000. And, or no, yes. Oh wait, no, 0 would, or 2000 would go to 1000 because zero base indexing. And 1999 would map to 999. And let's double check this. So if the value we have is 2000, we take -2000, add 1000 to it, you get 1000. So the complement of 1000 is -1000. That works. Let's think about this for now the other case. Let's look at -999. The opposite of that is 999 plus 1000 is 1999, and that gives you that. So that does make sense that this whole check thing works. And we're doing essentially all this did was make it so we pre-allocate all the memory we do, and our lookup is an O of 1 lookup. It's a guaranteed like check there. So I think that should work. So let's delete our old code down here, and we return solution. Let's see if we compile. Where do we screw up? Mathemax of solution and math absolute. Oh, I forgot a parentheses. That runs. Let's submit. And boom, we're in the like optimal 100%. Cool. That is such a fun way to like get the true optimization. So it's still like an O of, one, of n runtime, but this lookup here is such a fun way of doing that, and that took a second to figure out. Cool. All right, well, that's how you do, what's this called again? Largest positive integer that exists with its negative. To be honest, I don't think you would have to go this far in an interview. I think you could have taken our first solution and been perfectly fine. Um, I need to think about it more, why this is such a better lookup, and I think it's really in how we access the number because that's an O of 1, and there is like the potential that we have the hash misses on the other side that's causing um, the difference. But pre-allocating your memory is just another really small optimization that you can do to save time. So I hope this helps you. Hope you guys have a good one. See ya.